So let's sum up fitting with two regressors. When we have two regressors, the regression estimate for the slope of the first regressor is exactly the regression through the origin estimate, where we've regressed the second regressor, x2, out of y, and we regressed the second regressor out of x1. Okay? And so that makes a lot of sense to me, because it's like removing x2 from both y and x, and then only considering x1 in isolation and y in isolation, with x2 having been removed from both. So I think that's interesting, and it gives us a good way to think about what multivariate regression is doing. Also, I would add, when xi2 is the coefficient for it is exactly what you would get from regressing x1 out of y and x2, okay? Because there was nothing particular about choosing beta 1 to look at. We could have looked at beta 2. Okay, so we've actually done a case with two variables. Simple linear regression is an example with two variables, where here we specify our model. I'm going to specify it a little bit differently than we normally do, in that I'm going to specify that the second regressor is just a constant 1, is an intercept term. Okay? Then let's look at what happens here. Then look at what happens when your regressor is an intercept term. If x2 is just 1, just plug in 1 for there and there, then you wind up with, then multiply it times x2i, which is also 1. Replace 1 in all those three occurrences, you get that you wind up with x1 bar. And so the residual, having regressed out the intercept by itself, is nothing other than the centered variable. And similarly, there was nothing particular about choosing x1 to do first. We could have done y first. If we regress x2 out of y, we get the centered y variables. Okay, so regressing the intercept out of a variable, it turns out to just be demeaning the random variables. Okay? And so our beta 1 hat works out, I said, is this equation, those residuals. If we plug into them, then we get exactly the formula that we know and love at this point. Okay, so we've already done one example with two regressors. Now let's do general regressors. So I struggled a lot with trying to get a way to do this without doing any linear algebra, and I think I have a nice treatment. So let's go back. Hopefully you remember what, went too far. Hopefully you remember, let's see, there it is. Hopefully you remember these two equations, in that to get the least squares estimates, we said if we could get those two equations to be 0, then we'll have the least squares estimates. And it wound up with two equations with two unknowns, and look where we got it from right there. I'm hoping that you will believe me that if we have more than two regressors, we wind up with just a series of equations exactly like that. And that's what I have right here, is that we need to find a set of equations that satisfy that satisfy this root that we need. Okay, and so what this winds up with then is now p equations and p unknowns. Okay, and solving them yields the least squares estimates. But if you want a good, fast, general solution, then you need to know some linear algebra to get a general solution. And if you want it to be fast, you need to know some numerical linear algebra. But this point is interesting because it just generalizes what we did for two variables. The least squares estimate for the coefficient of a multivariate regression is exactly regression through the origin, with the linear relationships of the other regressors removed from both the regressor and the outcome by taking residuals. And because all we've developed is how to take residuals one at a time, you can do this one at a time, removing the linear relationship of x2, then x3, then x4, and x5 to get the adjusted relationship between y and x1. And it doesn't matter what order you do it, you just have to do all of them from both the y and the x1, and you'll get the multivariate adjusted case. So what that means is, in this sense, multivariate regression adjusts a coefficient for the linear impact of all the other variables. We've removed the other variables from both the regressor and the response. Which also tells us that if we'll see that there's then this special case if there is no relationship between a regressor and its the confounder that we're trying to remove. So again, this is another one of these details where you won't be quizzed or tested on, but I wanted to just show you how you get these things. So remember, we have these set of equations, and imagine if you held the first p minus 1 beta hats fixed, then you could solve for the pth one and you would get that estimate. And then if you plug beta p hat back into all these other ones, right, plug it in right there, then you wind up again with all of the residuals, ei of y given xp and so on, having regressed x of p out. But again, we have this guy right here, okay, x instead of the residual. But let me just show you that consider that equation right there. If we just reorder the residual definition, right, we get that equation right there, just reordering. Okay, and a fact that we've used often is that the residual, the sum of the residuals times the regressor is 0. Okay, so combine these two facts. So what we could do is for xk here, we could replace it with this expression right there. And then this expression, this part, is constant, and then this x sub p part varies. However, all of these residuals are given x sub p, and given that equation, when summed over, it goes away. So really, as far as this sum and all these residuals are concerned, we can just replace this x sub k by this x sub k given p, the residual given x sub p. Okay, so the long and short, let me move on to the next page. And if you're really interested in the details, you can go over the mathematics with a fine-tooth comb. But here's the end result. We've reduced p least squares equations now to p minus 1 least squares equations and p minus 1 unknowns. And then in that process, if you look at this equation, right, these sets of equations right here, wrong one, let me get it. If you look at this set of equations right there, it's exactly the least squares equations again, but only p minus 1 of them instead of p of them, and instead of y and a bunch of x's, it's the residuals of y having x sub p removed, and all the x's having x sub p removed, the linear relationship with x sub p removed. So we're at